Okay. Our next unit is on bonding, or how all of these elements combine into compounds. So this is chapter 7 and 8. All right, and before we start on this, we're going to do a real quick review of ions. Okay, so this is going to be a long paragraph, but I want you guys to write it down, and I want you to understand the language that is going into it. That's why I'm going to spend some time on this. In order to reach a minimum potential in order to reach a minimum potential energy state, atoms will gain or lose electrons to have an electron configuration like that of a noble gas. Okay. In other words, by the way, this is a good thing to have memorized. In fact, for my other periods, I made this list. Here, ETC is etc. This one you guys are probably most familiar with. Okay, and so on. EG is for example. IE is in other words. All right, so when you hear, football commentators totally blow these and mix these up, and give an example when they say IE and then they give an example, or they say EG and they re-explain what they're doing, that's because they're trying to sound smart, but they're not. Okay, it's one of those things. It bugs me. So just if you guys want to see that again, I can show you. But it's a good habit to have to know what those are. And we're going to use a couple of them right now. So, IE, which is, in other words, the highest energy levels, highest energy level, singular, S and P sublevels are filled. All right. E.g., for example, argon, okay, in other words, argon has, this is the electron configuration for argon. We've got 18 electrons, and these guys right here are highest energy level sublevels. Well, 1, 2, 3, these are our highest energy level. All right? And the highest energy level, S and P sublevels, both have the maximum number of electrons. Yeah? The 3s2, 3p6 means that our S block and our P block are filled, and we have, we have our highest energy level, S and P sublevels, filled. This is what it means to have a noble gas electron configuration, to have the highest energy level sublevels filled. Know what I'm saying? Okay. You got what I mean? Okay. All right. But other atoms try to do the same thing. Chlorine has this electron configuration. 1s2, 2s2, 2p6, 3s2, 3p, 5. It is 1 short of argon. It has 1 less electron, and its highest energy sublevels aren't filled. They don't have all of them. So what's it going to do? Okay, it's going to try and gain an electron. It's going to try and reach this electron configuration. And so right into this sublevel, we add 1 electron. Okay, when we do that, then we get our 3s2, 3p6, and our electrons in happy fun time. Right? We're at our lowest potential energy. It's cool. We can relax. We can Netflix and chill. You know. No, I know exactly what that means. Okay. So chlorine has 17 protons, but when we add our 1 electron, it now has 18 electrons. This gives us an imbalance of -1. We have 1 more negative charge than we have a positive charge, and that's what this charge counts. We have a -1 charge. So we write the ion as chlorine minus, okay, or chlorine -1, or chlorine 1 minus. Okay, but you usually, it's kind of like writing 1x in algebra. You kind of redundant, right? So you just write the minus. Okay. This also happens with metals and things over on the other side. Okay, number 19 over there is potassium. Thank you. Okay. Number 19 is potassium. Potassium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, it also does not have its highest energy level, s and p orbitals, filled. At least not for the 4th energy level. But check out right below the 4th energy level. It does, yeah? It's got that 3s2, 3p6, the s2 and the p6. Those are filled. Woohoo! That means that our 4s1, we can lose it. And we subtract 1 electron, and what are we left with? The 3s2, 3p6, right? Well, this is the same electron configuration as argon. It would be happy. It would, happy fun time. We have our noble gas electron configuration. It's all good now. Same thing with chlorine over here. It had the same had noble gas configuration. But this time, because we lost an electron, potassium has 19 protons. It now only has 18 electrons. Okay, and we have this. We have an excess now of which one? We have an excess of protons, right? We have more protons than our electrons, and that gives us a +1 charge. Okay, and because it's a +1, we would write potassium with a plus, K +1 or K1 plus, but same rules apply. If it's just 1, then we don't write it. Now, other things apply. If this was, for example, a P4, then we would add 2 electrons. If this was a 4s2, then we would lose 2 electrons. Either way, we're going to do what it takes to get to the s2p6 noble gas configuration. And whenever we lose those electrons, if we lose electrons, that's subtracting a negative, we get a positive charge. If we gain negatives, right? If we gain electrons, that's adding negatives, which makes it more negative. And we take, we get a negative charge for however many electrons we add. So that's how we get our charges for ions. This is why it happens. Now, okay, we have names for these, by the way, and I have not shown this to you yet. Okay, and it is, let me find the right pen here. This is a negatively charged particle. Can't see that? Oh. Okay, that is a negative ion. It generally comes from nonmetals. Okay, and we call these negatively charged ions that come from nonmetals. We call them anions. Get it? See what I did there? See the ends? You see that? Yeah. Yes. Okay. Yes. I did not give you this mnemonic yet. Okay. These guys over here. These are positive. Okay. Positive ions come from metals in general, and these are called cations. Cations. Okay, now they are not called cations. Okay, yes, they're spelled in a way that you could pronounce as cation, but that's the same way of saying that this word is ino. Yes, that's a possible way of saying the letter string OUGH is O, but that's not this word. This word is enough. So you don't say this is not cation, this is cation. This is not anion. Okay, even though if you switch the A with an O, it would become onion. This is not anion, it is anion and cation. Okay, it should be easy to remember to pronounce them with the ion at the end of the name, because what are we talking about here? Ions. So, call them ions. All right, we're starting with electronegativity today, and electronegativity is how unfairly an atom shares electrons with other atoms in a compound. Okay, and so what does this have to do with anything? Well, this governs bonding, okay, and how electrons bond. So, so bonding is the behavior of electrons between atoms. The behavior of electrons between atoms. Okay. And so what we look at with this is the difference in the electronegativity value between any two atoms. And the greater the electronegativity difference, the greater the electronegativity difference, the more likely the electrons will be owned by one of the two atoms. Okay. But you say, Mr. Allen, what electrons are you talking about? And then I say to you, I'm glad you asked. Okay, we are talking about the valence electrons. Okay, we're talking about our valence electrons. Now, which ones are the valence electrons?
The ones on like the outer ring,
right? Right, the ones on the outer ring, the ones that are in the highest energy level s and p orbitals, right? Well, wait a second. Didn't we just talk about that yesterday? S2, P6, P6, our S's and our highest energy S's and P's, those are our valence electrons. Okay, so if those are valence electrons, we're going to come up with a way to show our valence electrons in a really quick and visual demonstrative way that's going to help us understand where our electrons go. And these are called Lewis dot diagrams. Okay. Just about every element, particularly every main group element, all the ones in the S and the P block, do this. And so what I want you guys to do is to write the third period elements across. So we're going to draw sodium, and then magnesium, and then aluminum, and silicon, and phosphorus, and sulfur, and chlorine, and argon. And you need to leave a little bit of space between each one. Don't cram them all together. Space them out a little bit. We use our Lewis dot diagrams to illustrate how many valence electrons a particular atom is going to have. We're just looking at the outermost electrons, only the ones that are in the s and p orbitals. And the way we draw them is according to our Aufbau principle and our Hund's rule, like we've learned before. So, sodium. Sodium is way over there. It's number 11. It is in column 1. It is going to have how many valence electrons? 1. Group 1 over there has 1 valence electron. So sodium is going to have 1 valence electron. This one does not have to go on the top. It can go north, south, east, or west. It doesn't matter. Just pick a side. All right. It's a dot.
Oh.
This is a Lewis dot diagram. So we are drawing a dot, and the dot represents the electron.
Oh.
Now, sodium has 1.
Oh, God.
1 electron.
Oh, God.
Okay. All right. Now, magnesium's right next to it. How many valence electrons is magnesium going to have? 2. Okay. But if you think about this, that second electron is the s2 electron, right? So it's going to go into the same orbital as the first one. Yeah? So when we draw our first 2 dots, they go together. Now again, I draw my first 2 on top usually, just out of habit. It doesn't matter where you draw them, as long as the first 2 go together. Okay. All right. How about aluminum? 3. Hey, there's a pattern here. So, aluminum, we draw our first 2 together. I chose east this time. And then the next one can go in any one of the other 3 spots. Okay. Silicon's going to have 4, right? Next one over, it's in group 4. Silicon's going to have 4. Yeah? You with me there? Okay. Silicon's going to have 4. So, we draw the first 2 together. And then the next 2, however, according to Hund's rule, don't go together. Okay, remember that so we have one of them is an S2, and then the other three spots now are the p orbitals, and there's three p orbitals, and so this is an up, and that's an up, and we leave the last one blank, right? Okay, so let's draw the rest, and this will all come into focus. Phosphorus, how many electrons? 5, because we've had 1, 2, 3, 4, and 5, and it's in group 5 over there, so it's going to have 5 electrons. Pick a side. That gets the first 2. Then where are the other 3 going to go? And there's going to be 1 on each of the other 3 sides. So 1 here, 1 here, 1 here. Yeah? Okay, so there's 5 valence electrons for phosphorus. Okay, sulfur? If you guys can get ahead, go ahead and get ahead. Sulfur. Now, for the real process of this, remember it's 1 in each orbital, and then you have a pair, right? So 1 in each orbital, and then you have a pair. So sulfur would have two paired electrons and 2 unpaired electrons. Okay? Chlorine is going to have first 2. Once you understand the pattern and how they fill in, then you can just draw them around, and it doesn't really. You can just draw the 7. You don't have to draw them in any particular way, because no matter how you draw 7, you're going to have 3 sides of 2 and 1 of 1. Okay? Which brings us to argon. Argon has how many electrons? It's 8. It's got the it's a noble gas, right? It's got 8 valence electrons. 8 is our happy number, right? 8 is the happy electron configuration number, and so but here's what it looks like. Visually, can we put any more electrons there? Yeah. No, I mean you could just for the heck of it. But according to the minimal rules we have so far, this is full. This looks full, right? Yeah. Compared to what we've done so far? Okay, so this should feel right. All right, it looks, if you're filling up a noble gas, this should feel right. That it's got, it has the filled energy levels, right? Mm-hmm. Okay, so that's, now let's think back here. When we were making ions, we wanted the highest energy level S and P sublevels filled, right? That's why chlorine down here, with its 3s2, 3p5, is going to look like that. 7 electrons. But it's not done. It's not happy with the 7. It wants to look like a noble gas. So how is this chlorine going to look like an argon? It's going to add an electron. So if we add an electron, it's going to go right here. Voila. And all of a sudden, what does our particle look like? It looks like it. In our diagram, it actually looks like a noble gas. And that's because it's gained an electron. If it gains an electron, it has a -1 charge. Sulfur over here is going to want to do what? It's going to add to it. It wants to fill up its 8, right? So it's going to add 2 electrons plus 2 electrons, and that makes a sulfur 2-. Yeah? Phosphorus will be adding 3 electrons to make a P 3-. Okay. How about sodium over here? Are we gonna throw 7 electrons in there? No. And here's the trick. What does sodium look like underneath that 1 valence electron? Huh? It looks like neon. Or neon. Right. That's just how we say it in French. Neon. Underneath that 1 valence electron, it has one of those. It's got a full 8. It has a full set of 8 underneath this one. So when sodium loses its 1 electron, what does it look like? It looks like this again. But to do that, it lost 1 electron. That makes it Na plus. You subtract a negative, right? 11 minus a negative 1. No, don't do that. It's not 11 minus a negative 1. It's 11 electrons. Subtract an electron gives you 10 electrons. 11 minus 10 is plus 1.
No electron? I mean, an atom has no electrons.
Yes, but there's only one that does that, and it's hydrogen. The hydrogen ion has 1 electron. Hydrogen atom has 1 electron, and it will lose that electron to make its ion, and you get an H plus ion, but which is really just a proton. Well, what did we do? We gained 3 electrons. If we gain 3 electrons, our charge is going to be. So is that a 5 or a 3? Okay. All right. So these all want. So there's 2 things that happen here. Chlorine wants to gain an electron, right? These guys over here don't mind losing electrons. Yeah? So, when these guys over here form compounds with these guys over here, there is a transfer of electrons. These will actually give up their electrons so that they can be happy, right? All right, they can give up their electrons to make their ion charge here, and they give those electrons over to these guys so they can be happy, and they have their negative charge, and we have these ions that get made. And this is how the ions get made, is that the ones that like to give them up, give them to the ones that want to take them. Yeah? Okay. So you may be asking yourself, or asking me, well, Mr. Allen, what does that have to do with electronegativity? Well, I'll tell you. Okay? That if we have a large electronegativity difference, that ends up being a transfer of electrons. Okay? A small EN difference leads to a sharing. Leads to a sharing of electrons. So, how do we do, what does electronegativity have to do with this? When we look at our electronegativity table, we get this. Okay? And aside from row 7 down here, these are the electronegativity values of all of the elements. And if you remember your trend from last unit, that as we go left to right across the periodic across the periodic table this way, okay, that our electronegativity increases, and as we go down the periodic table, our electronegativity tends to decrease. All right. That creates a low region down here and a high region over here. Yeah? If you combine the trends, it creates this gradual diagonal. As you go this way, electronegativity should increase. This corresponds directly with the metallic versus non-metallic behavior of the element. And so these guys over here with a very low electronegativity value, okay, when combining with these guys over here with a high electronegativity value, okay, is going to create a large electronegativity difference. So let's say we look at sodium and chloride. Oh, hey, that's salt, right? Sodium chloride, NaCl. Okay. Chlorine has the electronegative difference of 3, has electronegativity of 3, and sodium has one of 0.9. If we take the difference, okay, taking the difference means we subtract 3.0 minus 0.9, we get 2.1. Now, that's how we find the difference. If we have a large difference in our electronegativity, we have an ionic bond. Okay. Ionic bonds form when the electronegativity difference, you guys know that change in electronegativity, the delta means difference or change, right? It's a triangle, means it's the Greek letter delta. When the electronegativity difference is greater than or equal to 1.9, we have an ionic bond. Leave a space here. I'm going to put something in here in between, but I'm going to do the other end first. Okay. The other kind of bond is a covalent bond. Let's break this down here for a sec. Co means together, right? Or with. Okay. Valent. Yeah, it has with our valence, right? We have the valence electrons, right? And valence shells. So a covalent bond is a bond where electrons exist in the valence shells of both atoms. You follow me there? That when two atoms combine, their orbitals kind of overlap and they smush into each other, and it creates it's called a molecular orbital. Ooh. Okay, and those are the regions where the electrons, the electron will actually go around both atoms now, not just one of them, and that creates an attraction between two elements. This is called a covalent bond, and a purely covalent bond has an electronegativity difference that is less than 0.5. Or actually, we'll call it 0 and equal to. Well then, that's a pretty big gap in between, right? Mm-hmm. Okay. Well, this is where the sharing analogy comes in, with the unfair sharing of your video game. In between, we have an electronegativity difference that is greater than 0.5, but less than 1.9. If it's in between, it is called a polar covalent bond. And it is an in-between state. It's not quite taking the electrons away like it was over here, but it's not sharing them equally like it would be over here for the covalent bond. A polar covalent bond is an unequal sharing of the electrons. Does that make sense to you guys? Okay, and that the more electronegative, now it's still kind of going around both of them, but it kind of looks like this. Here's one atom, here's another one, and the orbital shape is kind of like this. Okay, where one of them has, remember it's a probability space, right? These regions that we draw are, this is a tough thing to shade. The probability space is where we would probably find that electron, right? 90% of the time, an electron, if it's in this covalent bond, it's going to be in this region of space. That means that if we have this electronegativity difference, most of the time it's going to be around one rather than the other. And so the region of space is going to be larger around the other one than it is, larger around this one than it's going to be that one. You guys follow me there? Okay. So these are our three types of bonds. Okay, we have ionic, polar covalent, and covalent. There's another one called a metallic bond, but it plays by different rules, so we're not gonna deal with that for right now. All right. So your assignment today is, okay, and what your homework is based on is, I want you to find, merely based on electronegativity difference, find me a pair of elements that will share an ionic bond. Find me a pair of elements based on electronegativity difference that will share a polar covalent bond, and another one that's just going to be covalent. Okay, and I will give you a hint. It is okay if you choose two of the same element. Okay, or actually here, the example I'll give you is chlorine, for example, is 3.5. Yeah? Or here, no, I'm sorry, not 3.5, it's 3.0. Chlorine here is the 3.0, right? Two atoms of chlorine, okay, here's a 3.0, right? Here's a 3.0, and here's a 3.0. The difference between them is 0. That would be less than 0.5, right? Yeah? So the bond between two atoms of the same element would be a purely covalent bond. Yeah? Okay, I'll give you a hint. The covalent bonds only happen with nonmetals. We'll don't do any metals with this one. That's just sort of a little hint right there. But that's your homework for tonight. So that's find 3 pairs. It's really pretty straightforward, but I want you guys to find 3 pairs. And then, and I need to put this in there, then hypothesize a model that describes the differences in bonding that doesn't mention electronegativity. In other words, see the pattern. Look for patterns with these, okay, and try and come up with another way of determining whether something's going to be an ionic bond, whether it's going to have a polar covalent bond, or whether it's going to be a covalent bond. Okay, without using electronegativity to explain it. After what? Differences in bonding. Hypothesize a model that describes the differences in bonding that doesn't mention electronegativity, but I'm going to put that into your Google Doc. Okay, that's it for today.